Now we're going to look at the rational root theorem. Now we've been spending a lot of time finding roots and solutions to different types of equations. We learned how to factor, we learned how to solve quadratics, we learned how to solve different types of cubic functions, we've been learning how to divide polynomials, we learned Descartes' rule of signs, we used conjugate root theorem, all of these things related to finding and explaining the different types and variety of roots that a function has. Now the whole point is that we want to be able to find roots and solutions, or sometimes called zeros, for any polynomial that comes our way. Now we've been building up our toolbox for these types of problems that are difficult. So far, the different types of cubic polynomials that we've solved have been cubic polynomials that we could factor and then break down into a quadratic function. And then we used all of our different methods of solving quadratics to solve that part of the cubic function. Now, whenever the cubic function is not factorable, we have no way of actually solving them. But what we're going to do now is look at a different method of solving those types of cubic functions, as well as any other higher order polynomial. So let's take a look at this quadratic function. So the easiest method to solve this quadratic would just be to factor. So factoring, you can see that you set each linear factor equal to 0, and then here are our roots. Now hopefully you can see some type of pattern between what our roots look like and what the original polynomial was. It seems like the denominators of our roots come from the factors of the leading coefficient here. The numerators of our roots come from the factors of the constant. Alright, so here we go. The rational root theorem is going to help us find all of the rational roots that are possible for a polynomial. Now, this word possible is very important. I want you to understand that this is just telling us all the different rational numbers that could work. Now, it doesn't mean that they do, and it doesn't mean that the answer is in that list, but it means if a rational root exists, it will be in that list. The rational root theorem says that anytime I'm given a polynomial p of x that has integer coefficients, in order to find the possible rational root, so remember this word possible means that if a rational root exists, it will be in this list of numbers. We take the factors of the constant term and we divide it by the factors of the leading coefficient. So remember, in standard form, the leading coefficient is the number that is at the very front of my polynomial. Now, we cannot forget the positive and negative factors. So I want you to think about the number 12. If I'm looking at the number 12, what are the factors of 12? Well, I have 12 and 1, I have 6 and 2, and then I have 3 and 4. Now, how else can I make 12? Well, I can do negative 12 times negative 1, negative 6 times negative 2, negative 3 times negative 4. So you can see that my list of possibilities are positive and negative, which means if I wanted to list all the factors of 12, I would say that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So we have to consider positive and negative factors. So, for example, on the last slide, we already looked at the factors of 12. So now let's look at the factors of 10. Now the factors of 10 are going to be plus or minus 1, plus or minus 2, plus or minus 5, and then plus or minus 10. Now, if I want to look at the possible rational roots, it's the constant factors divided by the leading coefficient factors. Okay? So, that means I take all my constant factors and I have to divide them by each of my individual factors for 12. Which means plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 2, plus or minus 1 over plus or minus 3, plus or minus 1 over plus or minus 4, plus or minus 1 over plus or minus 6, plus or minus 1 over plus or minus 12, So all I did there was take this plus or minus 1 and divide it by all of the factors of 12. Now, I'm not done, because now I need to do the exact same thing with plus or minus 2, the exact same thing with plus or minus 5, and the exact same thing with plus or minus 10. So you can see that the list of possibilities is very great, but compared to the infinite amount of numbers that exist, this list is relatively small. So we at least have somewhere to begin when we are searching for roots. So remember, you need to put all of these factors over each constant factor over each leading coefficient factor. So it's a rather large list of numbers whenever you have numbers that have many factors. When you're making your list of possible rational roots, I want you to be aware of any duplicating. So now when I go plus or minus 2 over plus or minus 1, I don't have that already. But plus or minus 2 over plus or minus 2 is the same as saying plus or minus 1 over plus or minus 1. So I don't need to write that again, okay? But I don't have plus or minus 2 over plus or minus 3. Now, plus or minus 2 over plus or minus 4, again, is the same as plus or minus 1 over plus or minus 2, so I don't need to write that one again, okay? Plus or minus 2 over plus or minus 6 is the same as plus or minus 1/3, all right? So anytime you have duplicates, you don't need to write those. So that makes our list even smaller. So here's our entire list of possible rational roots with no repeats. I'm sure you're wondering how we narrow down this huge list to figure out our root. Well, remember, if a is a root, then x minus a represents that root as a linear factor. Now, if x minus a is indeed a factor of the polynomial, then we divide it, we should not get a remainder. So one of the methods we're going to use is using synthetic division. We're going to be dividing these linear factors and hoping that we find one that does not have a remainder. Now, once we do this, we're going to continue until we eventually have a quadratic function that we can solve using one of the methods that we've learned. Now, this includes quadratic formula, factoring, square rooting, any method that we've learned that we can apply. All right, so let's find the factors of the constant term, factors of the leading coefficient. This time will not be as many. So to find the possible rational roots, we need to take all of these values and divide them. So pair them up, pair them up, pair them up, pair them up with division. And we do not write any repeats. The next step is you can use Descartes' rule of sign to help you narrow down from this list. So let's look at the sign changes. So for positive real roots, we look at the sign changes. Well, right now we have plus, plus, minus, minus. So we have one sign change, which means I have one positive real root. Let's look at the negative sign changes. Well, this is going to change to minus. This will stay the same. This will change to plus, and this will stay the same. So that's 1, 2 sign changes. So that means I have 2 or 0 negative real roots. Why is this helpful? Because I know for sure, 100%, I have one positive real root. So when I start checking through this list, it might be a smart idea to start checking all of the positive roots first before you start looking at the negative possibilities, because I know for sure I have one positive real root. So now is the part where we just have to start guessing and checking. Now I know for sure I have one positive real root, so I'm going to start and do all the positive possibilities first. So choosing 1, put 1 in the box, 2, 1, -7, -6. And then we just synthetically divide to see if I get 0 remainder. Now at this point, you should be able to tell that this is not going to work. All right? So I just cross that out. It's not going to work. I go to my next possibility. Now I'm going to do the whole numbers first. does not mean that you won't have a fraction for one of your answers, but I just choose to do the whole numbers first. You can do it whatever order you want. So again, we set it up. Ah, look at that. I have 0 as a remainder. So now what we do is we look at this function here that is left over. So remember, remainder, constant, linear, quadratic. So this is going to be 2x squared plus 5x plus 3 is the leftover factor to my polynomial that I began with. So we have a quadratic, which means I can stop because I know how to solve a quadratic function. So here's my quadratic function. Now we're going to use one of our methods to solve quadratics to find the rest of my roots. Now, if it's factorable, that's going to be the easiest way. So let's check if it's factorable. I think this one's going to end up being factorable. Factors of 3 are 3 and 1, but I want to make 5 in the middle. So 3x, 2x. So yes, I will get 5 in the middle. Same, both positive. Now what this means is you set each of these equal to 0. So 2x plus 3 equal to 0. My x is going to be negative 3/2. X plus 1 equal to 0. X is going to be negative 1. So I found all of my roots. My roots are, remember before we found the root of 2. So my roots are negative 3/2, negative 1, and positive 2. I should have 3 roots because I started with a cubic function. Remember, fundamental theorem of algebra. Now another way to narrow down your possible rational roots is to use the remainder theorem. So remember, the remainder theorem said that if a is a root, then when I plug it in, it's going to be a factor of the beginning polynomial if I get 0. So if you were to look at the equation we were just looking at, for 2, when you plug in 2 everywhere you see an x, you get 0. So that would have also triggered to me that 2 was a root. Now, if you did that, that's fine. But then remember, you still have to go ahead and synthetically divide to find that leftover quadratic function that you have to solve. Go ahead and give this a try on your Google form. If you have to use plus minus, just type plus minus, or you can say the words plus minus.